Check it out now, y'all.
NanoHub U, online instruction.
So welcome to tutorial 1.1, so in week 1, and this first homework problem, this 1.1, it's just designed to give you some practice with how to keep track of units. As you know, in science and engineering, that is a very important skill in general. And we started with, the example I give is I ask you to calculate this quantum of conductance. Because in this field of nanoelectronics, one of the important concepts that you'll see a lot of, one of the important quantities, is this Q squared over H. This is the quantum of conductance, and Q is the charge on an electron, H is the Planck's constant. And you want to evaluate how much this is. And if you put in the numbers, like Q, I think it's listed on your homework, the value for Q is 1.6 times 10 to the minus 19th coulombs and Q squared, so could write again 1.6 times 10 to the minus 19th divided by H, which is this Planck's constant, and the value it's up there, I believe, is 6.626. I guess for our purpose, 6.63 would have been fine. 10 to the minus 34 joule second. That's the units of Planck's constant. Planck's constant is energy times time. It's joule second. And this Coulomb square. Now, finally, of course, we are calculating conductance. As you know, conductance is like the ratio of current to voltage. And current is amperes, voltage is volts, and amperes per volt, that's what is usually denoted as Siemens. So what you want this quantity should have the dimensions of amperes per volt, but that's Siemens. So one thing you could check is in these units, does it look like amperes per volt? Well, what you can check is, you see, this Coulomb per second, that's like amperes. You see, Coulomb is charge, ampere is charge per second, so that's Coulomb per second, that's amperes. And this Coulomb per joule, you see, that's charge divided by energy. And energy is like charge times voltage. And so Coulomb per joule is like 1 over volt. And so what you have is amperes there, and Coulomb per joule is volts. So what you have is amperes per volt, and the answer is in Siemens. So the rest of it now is simply about getting the actual numerical value. The units are all looking right. In general, you don't really need to check units if you are doing everything in MKS. If everything is in MKS, then the answers would also come out in MKS. And you normally don't have to worry about this. One thing you'll see is when we deal with energy, we'll be often using a unit that's not really MKS, and so you have to be a little careful. Anyway, in this context, I was just showing that the units do come out right if you worry about it. Next, we just want to get the numerical values. So it will be 1.6 times 1.6, that's 2.56, divided by 6.626. And then you can collect all the powers of 10 together, and you'll see it's 10 to the power minus 38 divided by 10 to the power minus 34. So that comes to 10 to the power minus 4. So you can see roughly the idea that this is about 1/3, roughly, and then 10 to the power minus 4. So, and that's Siemens. And if you actually now put in the numbers, I think the answer you'll get is 38.6 times 10 to the power minus 6 Siemens. And you can roughly see the idea that 10 to the power minus 6 times 100, and this is like 1/3. So 100 divided by 3, roughly on that order. Roughly see that. Now, and this is 10 to the minus 6 Siemens is what you often might write as microsiemens. Anyway, so that's then the quantum of conductance. Now this is part A of the problem. Now in part B, that's kind of follows trivially in the sense, what I ask you to do is find H over Q square. That is, instead of Q square over H, I ask you to find the quantum of resistance, which is H over Q square. And that, of course, is just the inverse of what we just calculated. So it would be 1 divided by 38.6 times 10 to the minus 6th Siemens. And the inverse of Siemens would be like ohms. That's the unit of resistance. So this would come to about 10 to the power 6 divided by 38.6 ohms. And if you put in the numbers, I think it will come to about 25.9 times 10 to the power 3 ohms. And that's like a kilo ohm. So that's the quantum of resistance, about 25 kilo ohms. See? Now, part C, what I asked you to do is find kT. That is this unit of thermal energy, the one that appears in the Fermi function. It's something, again, you often see a lot of. So let me just go through that one. Take off this. Now for kT, so K is Boltzmann's constant, which is this 1.38 times 10 to the power minus 23 joules per Kelvin. And T is the absolute temperature, and usually for room temperature, people use 300 Kelvin. It's room temperature, which is about 27 degrees centigrade. Now, if you multiply by, say, 300 Kelvin, then you'd get your answer in joules. So that's all there is to it in terms of getting it in joules. The thing is that when you talk about energy, it is quite common to use electron volts instead. And if you want to convert it to electron volts, then what you need to do is divide this by the charge on an electron, which is 1.6 times 10 to the power minus 19. So this is in joules, that's MKS units. But for energy, it is much more convenient to be talking in terms of electron volts. And for that, you have to divide by 1.6 times 10 to the minus 19th. And if you do that, the answer you will come up with, this will now be in electron volts. And so I guess you could view this as joules per electron volt. So the joule cancels and you get overall in electron volts. And the answer will be 25 times 10 to the minus 3 electron volts. And this is like a milli-electron volt. So again, this is a number that people who work on devices, something they carry in their head usually. What's kT at room temperature? Well, about 25 milli-electron volts. Now that brings me then to the last one, number D, which is, let me do it here. They say is, if you have an electron whose mass is just a free electron mass, so the kinetic energy is say half mv square, and you're given that the energy of an electron is 10 milli-electron volts. And what you'd like to do is figure out what velocity corresponds to that. What its velocity must be, assuming that it's got the free electron mass, it's a free, what velocity would be to give it that much energy. And the energy is 10 milli-electron volts. So the way you'd write it is 10 times 10 to the power minus 3 electron volts. And if I want to get it back into MKS, I'd multiply it by 1.6 times 10 to the minus 19th. So the energy is 10 millielectron volts, which is equal to this quantity times this joules. Okay. So now I can find V squared as, if you take the 2 over there, times 1.6 times 10 to the power minus 21. I believe I collected those things together. And I divided by the mass of an electron, which is 9.1 times 10 to the minus 31. So now you see everything is in MKS, and the answer should come out also in MKS, which is meters per second for velocity, and velocity square should be meter square per second square. And if I take this quantity and then take its square root, I believe you should get something. What I got was 5.9 times 10 to the power 4 meters per second. So a free electron traveling with a velocity of about 6 times 10 to the 4th meters per second that would correspond to a kinetic energy of about 10 millielectron volt. Again, the purpose of all this is to give you some practice with how to change units and keep track of these. Okay, that's it.